So far in Chapter 7, we've talked about some gas properties. We've mentioned a few named gas laws as well as a combined gas law. But this part of Chapter 7 here is where we're really going to bring it all together, and we're going to combine all of those details from the prior chapter sections into an overarching idea about how gases behave. Now, we've mentioned before that gases don't quite exactly behave ideally, so although they do a pretty good job of obeying the rules we made for them, this section here, the ideal gas law, which combines the ideas of volume, pressure, number of moles, and temperature all at once, only holds for ideal gases, although it holds pretty well for real-world gases. So we can't quite say without exception that this ideal gas law is going to be upheld in nature, but we get pretty darn close to ideal behavior out of most gases. Okay, so the ideal gas law takes those four properties we've discussed, pressure and volume we talked about with Boyle's law, and then volume and temperature we talked about with Charles's law, and volume and number of moles most recently with Avogadro's law. In addition to those individual laws and even the combined gas law we had earlier where P1 V1 over T1 equals P2 V2 over T2, if you recall that, now we can have an ideal gas law that gives us a single expression that even accounts for the number of moles, N, which was missing from that combined gas law earlier in the chapter. So this ideal gas law is pretty rhythmic. It's really fun to say PV equals nRT. You get really used to it. It's fairly easy to memorize for even those of us who have memories that are failing in our advanced years like me. PV equals nRT is a very nice, concise formula. It rolls off the tongue. It's pretty easy to memorize, and it's pretty powerful stuff. Okay, so probably what you're thinking about is that R, right? That's the one thing we haven't talked about yet. We've talked about pressure and volume and how they're inversely related. We've talked about volume and number of moles and volume and temperature as being directly related in our various gas laws, but we never mentioned this R before that came up in the PV equals nRT, and that's because R is the constant, the ideal gas constant to be exact, and it's that factor that relates all of that. So for the value of R, if we look at STP, which we've talked about as standard temperature and pressure, we know that volume of any gas at STP should be 22.4 liters, at least an ideal gas. And again, most real gases, at least at standard temperature and pressure, behave pretty ideally. So we know that that's 1 mole of gas at 22.4 liters for standard temperature of 273 K and standard pressure of 1 atmosphere. Having all those values, we can solve for R, and one form of R is 0.0821 liter atmospheres per mole Kelvin. That's what we call the gas constant form of R. There's another thermodynamic form of R that we might touch on later, but this is the form of R that we care about here for Chapter 7 on gases. Okay, so we just hit you with this constant, and we're already going to do a learning check and see how you do with this. So again, the constant R is equal to 0.0821 liter atmospheres per mole Kelvin. We can get another value for that universal gas constant R if we use millimeters of mercury instead of ATM for standard temperature and pressure. What is the value of R when a pressure of 760 millimeters of mercury rather than 1.00 atmosphere is used? So pause the video here. Hopefully it won't take you very long to see the trick to this, and then start back up once you think you've solved it. Okay, so of course, if you're going to solve for R, you need PV divided by NT. And so here for P, instead of the 1.00 atmospheres, we're going to put 760 millimeters of mercury. Volume is still 22.4 liters for 1 mole at 273 Kelvin, and standard pressure, this time expressed in millimeters of mercury instead of atmospheres, and therefore we get a value that is 62.4 liters times millimeters of mercury divided by moles times Kelvin. So again, we ultimately just multiplied that 0.0821 liter atmospheres per mole Kelvin by 760 to convert the atmospheres into millimeters of mercury. So it may have taken you a little while to catch that, or maybe you gave up because you didn't catch on fast enough, but hopefully really, now that you've seen it, it's not a terribly difficult idea. It's just a unit manipulation, a unit conversion of atmosphere into millimeters of mercury. And so here we see a unit summary for R, just using those two different values. First of all, the form that's more common, the 0.0821 liter atmospheres per mole Kelvin, because we tend to use those units to describe gases, so that tends to be the form of R that we use more commonly. And then, as we just saw, if we use millimeters of mercury instead of atmospheres for pressure, then we've multiplied that by 760, and we end up with a value of 62.4 liters times millimeters of mercury divided by moles times Kelvin. So you may see it in that form occasionally, but honestly, the 0.0821 is the much more common form because the atmosphere is the preferred pressure unit in chemistry. All right, so now that we have this new equation, the ideal gas law, we have a slightly modified guide. It's a three-stepper, which is welcome news since last time, I think in the previous section, we were doing a four-step guide. So fewer is usually better, right, from a student view anyway. So number one, like usual, we'll state the given and needed quantities. Number two, we'll rearrange the ideal gas law equation to solve for whatever the needed quantity is. And then number three, we'll substitute in the gas data and calculate the needed quantity. Okay, so rather than working one together, let's see if you can do that on your own, right? You're getting to be pros at this. We're more than halfway through the course, so let's see how you do with a learning check first. This learning check says dinitrogen monoxide, technically, if we want to give the actual name, nitrous oxide as it's commonly called, laughing gas, is used by dentists as an anesthetic. If a 20.0 liter tank of laughing gas contains 2.86 moles of N2O at 23 degrees Celsius, what is the pressure, millimeters of mercury, in the tank? All right, so hopefully you can take this information from the problem and use the ideal gas law to solve for the pressure. Okay, pause the video here and start it back up once you think you've arrived at the answer. Okay, so applying our steps here. In step one, we're going to state the given and needed quantities. And as we analyze this problem, we find that pressure is ultimately what we need. And this question specifies that we report that in millimeters of mercury. We're told the volume of the laughing gas is 20.0 liters. It is 2.86 moles. The form of R to use would be the 62.4 liters times millimeters of mercury per mole times Kelvin, because ultimately we want millimeters, but certainly you could use the 0.0821 liter atmospheres per mole Kelvin, and then at the end convert from atmospheres into millimeters of mercury if that's the way you prefer to do it. And finally, temperature here is given in Celsius, and so we need to add 273 to arrive at a Kelvin temperature of 296 Kelvin. Moving on to step two, we can rearrange that ideal gas law so that we can solve for our needed quantity. So of course, the more usual form, the form that rolls off the tongue, PV equals nRT. Well, if we divide both sides by volume, then we can solve for pressure as we need to in this example. Moving on to step three, we can substitute in the data and solve the equation to find a final value of 2.64 times 10 to the third millimeters of mercury. So hopefully it wasn't too difficult. And again, if you had selected the 0.0821 liter atmospheres per mole Kelvin, you'd end up with an atmosphere volume or pressure rather, that you'd ultimately convert into the same 2.64 times 10 to the third millimeters of mercury, or 2640 if you kept it out of scientific notation. If you weren't able to solve it or made some mistake that you're really not sure what went wrong, please do reach out to me, but hopefully it wasn't terribly difficult to solve this thing first before we worked one together. Another way we can do this is to combine the ideal gas law and molar mass. So combine those two ideas, and instead of solving for, say, just N for the PV equals nRT, we could solve for the mass, knowing that once we get N, we would multiply through by that molar mass. So it's still a three-step process. We're still doing the same things in part one. In part two, we're probably if we're solving ultimately for molar mass, part 2 is going to involve, instead of solving for pressure like we did in that first learning check, instead solving now for number of moles, and then once we have those number of moles, multiplying through by the molar mass to give us the gram mass of that particular gas. So let's go ahead with another learning check, see how you do without us having to solve one together first. Let's see how this goes if you're just thrown into it to solve the learning check that specifies a cylinder contains 5.0 liters of an unknown gas at 20.0 degrees Celsius and 0.85 atmospheres. If the mass of the gas in the cylinder is 5.8 grams, what is the molar mass of the gas? So again, we'll be looking for moles here, but then we'll be finding the molar mass of the gas by taking those moles and dividing through by the mass. So pause the video here, work it out, and once you think you have the correct answer, start us back up and we'll see how you did. Okay, so like we always do, we'll start with analyzing the problem, and we see here that we're given the value for volume as 5.0 liters. We're given pressure as 0.85 atmospheres. We're given temperature in Celsius, which we need to add 273 to convert to Kelvin, and we do that to find 293.0 K as our Kelvin temperature. For number of moles, that's what we're looking for, and we know that the ideal gas law requires that ideal gas constant. In this case, since we have pressure in atmospheres, we'll use the 0.0821 liter atmosphere per mole Kelvin form of the ideal gas constant. Moving on to step 2 here, we can rearrange that ideal gas law, PV equals nRT. Now if we're solving for N, we need to divide both sides by RT, so we get N equals PV over RT. If we substitute in those values that we have from the problem, and again, pay attention to the units, we should end up with 0.18 moles of this unknown gas. So now in our final step, we can find the molar mass of that unknown gas by taking the 5.8 grams of gas that we're told in the problem as the mass of the gas in the cylinder and dividing it through by the 0.18 moles of gas that's present, and we find that it is a mass of 32 grams per mole, and possibly maybe oxygen gas would be a likely candidate having that 32 gram per mole, although without any other information we really can't make any necessary identity assignment for this unknown gas. Now I know exactly what you're thinking, and it's everything's been too easy up until now, right? So let's complicate things a little bit, and let's deal with chemical reactions in the ideal gas law. So now we're up to 5 steps here. The first step is still the same, stating those given and needed quantities. The second step is similar to what we just did, where we're writing our plan to find moles. Then the third step is going to involve those equalities for molar mass or mole factors, depending on the specifics of the reaction and the information given. Then finally, we can set up a problem to calculate moles of needed quantity, which is probably a different reactant or product than what we're given initially. And in our last step, we'll convert those moles to mass or volume using the molar mass or ideal gas law equation, depending on the particulars of the problem. So why don't we follow up with another learning check and see how you do on your own. Okay, so in this learning check, we see that nitrogen gas reacts with hydrogen gas to produce ammonia gas. How many liters of NH3 can be produced at 0.93 atmospheres and 24 degrees Celsius from a 16.0 gram sample of nitrogen gas and an excess of hydrogen gas? And we're given the balanced chemical equation to see those mole-mole ratios necessary for the nitrogen and hydrogen to react and form our ammonia product. So go ahead, stop the video here, solve the problem, and start back up to check your work. All right, and step 1, of course, we're analyzing the problem as we always do. So we see that we're given 16.0 grams of nitrogen. That's going to be our limiting reactant because we're told we have excess hydrogen. We need to know how much product we can make at 0.93 atmospheres. So we're ultimately looking for the liters of NH3, and we're at 24 degrees Celsius, which we have to convert into Kelvin to find a 297 Kelvin temperature. Our equation, our balanced chemical equation, is going to be very useful for figuring out how many moles of ammonia we can make from that many moles of nitrogen. Moving on to step 2, we can write our plan. So we'll start with those grams of nitrogen. We'll use the molar mass of nitrogen to find the number of moles of nitrogen, and then using the 2 moles of NH3 produced for every 1 mole of nitrogen consumed, we'll be able to convert into moles of ammonia gas. Ultimately, from there, we'll be able to find the liters of NH3, which is ultimately what the question is asking for. In step 3 here, now we can write a few of those equalities and then find the necessary conversion factors to get the unit cancellation that is desired. So 1 mole of nitrogen equals 28.0 grams. Because it's a diatomic, of course, we need to multiply that 14.0 times 2. We know that 1 mole of N2 gives rise to 2 moles of NH3 when it's reacted. Then we can, of course, have those equalities represented as conversion factors with either species in the numerator and denominator as needed to cancel units in our dimensional analysis scheme. Now in step 4, we can set up the problem to calculate the moles of the needed quantity. So here we have 16 grams of nitrogen multiplied by 1 mole of nitrogen over 28.0 grams of nitrogen. And now that we're in moles of nitrogen, we can convert to moles of ammonia by using the balanced chemical equation to show that 2 moles of NH3 are produced for every 1 mole of N2 reacted. And we get a value of 1.14 moles of ammonia. Now in step 5, we can take that value of the 1.14 moles of ammonia and we can find a volume value for it by rearranging PV equals nRT, dividing both sides by P to isolate V, and we get V equals nRT over P, plugging in the 1.14 moles of ammonia gas that we would produce, the ideal gas constant form of 0.0821 liter atmospheres per mole Kelvin, multiplying through by that 298 Kelvin temperature, we find that we should be able to produce 29.9 liters of ammonia from the complete reaction of that nitrogen with excess hydrogen. So there you have it. Hopefully you got there on your own. If not, hopefully you understand the steps involved now as we worked it through together. If you're still lost completely, please do reach out. This isn't going to get any better on its own. It's not going to go away, so please do reach out for help. But otherwise, if things are going swimmingly, as I hope they are, we will see each other again for the last section of Chapter 7 in the next video.